Okay, so let's get started. I'm very honored to be the speaker at the CIDER. It's my first CIDER, and I'm learning a lot. Not only because I get a chance to work with and learn from outstanding colleagues, but I'm thinking many of you in the student going to make a distinguished career from here and moving on. I'm nowhere as smart as some of the physics, geophysics colleagues thinking in 3D and 4D. And I'm simple-minded, so I'm going to only work on 1D, which is time, and it's unidirectional, right? And we also know that timing is everything, right? So here's one way that I tell my astrophysics colleague that we actually also use mass spectrometer as a poor man's telescope. In fact, it's a pretty good telescope. You can actually look deep down in planet's core and look back 4.5 billion years ago and even beyond. And we can look at actually many stars and its deep interior. And best of all is timing of all the processes. And if you look at the astrophysicist telescope, they're only looking at photons and light, right? So here's me operating mass spectrometer. So here's where I'm going with today's talk. First, I'm going to give you an inventory, chemical inventory that we inherit from stellar nucleosynthesis, talking to Bill White, that he suggested I should talk a little bit about that. Then I will briefly talk about, in 2 or 3 slides, a free-fall time and trigger star formation and planet formation, why that is important, and what we learned from Cosmochemistry about that aspect. Then I will describe planet formation processes, a standard model right now, sort of very similar to free market economy, and I will explain why that is. Okay. And then I will explain how the extinct radioactivity works as a chronometer, especially as a very high resolution chronometer at the beginning of the Earth, which set the stage for the rest of the evolution. Then I will give examples from each major stages of planet formation from chronological aspect. Then I will conclude. So that's my outline. So here's a cosmic abundance of chemical elements. This is coming from Stan Woodsley's Nature Physics, but it's actually the first compilation of these data is done by Goldsmith along this very similar fashion, and he called this graph as his Ninth Symphony. And actually, this graph leads to at least 3 or 4 Nobel Prize and Crawford Medal and so on. So what this graph tells us is that hydrogen, helium, and maybe a little bit of lithium is created during the Big Bang nucleosynthesis from time 0, right? And all the rest of periodic table are done in the stars. So we have a coffee here. Hydrogen is 13 billion years old, and the oxygen, which make up water, is who knows how old they are, but at least they are older than 4 billion years and younger than 13 billion years. Sometime later in the history of the galactic chemical evolution, you make this. So when you look at that, all this zigzag pattern is one other reason chemists need to normalize things, right? Otherwise, you will deal with all this up and down and up and down. And there is a good reason for that. It is even isotopes are more stable than the odd ones. All right. So here's a chemical inventory, galactic chemical evolution. So you started with hydrogen and you start with helium. This is what astronomers call X and Y. So you have 71% of hydrogen, and then helium is 27%. And the rest is Z. It's astronomers' metal. And from lithium to uranium, it's only 1.49%. And out of this Z, 1.49%, CNO plus neon dominate more than half of the Z. So if you look at carbon and oxygen budget within our own solar system, we have 0.247% of carbon and oxygen 0.65%. It turns out that the carbon monoxide is the most stable and most abundant molecules next to hydrogen, H2. So we really celebrate our good fortune. Actually, in our solar system, in our neighborhood, we had this excess oxygen here, right? Imagine 4.5 billion years ago, just by sheer accident, that a carbon star blow off nearby, then we will be basically all the oxygen will be locked up in CO, carbon monoxide, and we'll be in a carbide world, right? So you can have a diamond planets, et cetera, but we will not have silicated rock to stand on, et cetera. Yeah.
You're talking in atom percent, not weight percent?
This is a molar percentage, yes.
This is weight percent.
This is weight percent? Okay. But anyway, this is a little excess of oxygen, okay? And then with all this time the galaxy universe had, with all the power and time and pressure and temperature, and universe only managed to convert the original inventory of hydrogen and helium into Z, just 1.5%. You have 13 billion years to work on. So it's kind of, each time when I look at this graph, I kind of very pessimistic about hydrogen fuel efficiency. Right? So in terms of nucleosynthesis, this is a very useful way to look at it. What I have done here on X or Y axis is a binding energy. So you just count number of protons for each element and count number of neutrons of each element, and then you add them up, and that's the total mass. And then you look at the real mass of each nuclide, and there is a mass differences. And that mass difference is converted into using E equals mc squared and converted into energy. And when you divide all the elements up and plot all the periodic table up, what you see is this curve. So what you see is anything below iron, lighter than iron, what you have is as nuclear fusion proceed, it is an exothermic reaction. So the more you do nucleosynthesis, the more energetically favorable. You are releasing more energy, and then it triggers next stage and triggers next stage. So it keeps going on when you have infinite amount of mass, big enough to proceed all the way up to iron. So basically, this part of the periodic table is pretty much done by nuclear fusion. So you have hydrogen fused into helium, and helium into 3 helium into carbon 12, and 4 helium into carbon 16, oxygen 16, et cetera, silicon. And you can proceed all the way. And when you hit the peak here, up to the iron, then all of a sudden, right, it's no longer energetically favorable. So you're not producing energy anymore, and you're consuming energy, right? So when you actually start with a big volume of hydrogen and then manage to convert into very small volume of iron, right? And the time scale is here is about 10 billion years, and here is like a few seconds. So all of a sudden, you run out of energy and you start to consume the energy. Then basically the collapse, that you have no power to actually counterbalance, no temperature and pressure to counterbalance the enormous static pressure from the envelope of stars. So when that happens, the collapse happens. That's the end of the star's formation. So anything beyond iron is done by so-called neutron addition. So in that second or so, the rest of the periodic table is made, and then of course you go through this many stars, and solar system 4.5 billion years ago just happens to inherit whatever you have. So to summarize, from hydrogen to iron, the nucleosynthesis path is almost like a hydrogen bomb, and anything in the heavy elements, it's like a uranium bomb. It's a fission because you cannot add infinite amount of neutrons because a nuclear binding force is a short-range forces. So when you have too much, then you lose the stability. So you cannot add infinite amount of neutrons. So you will never have super heavy elements. So nature made all the way to bismuth, and uranium and thorium is next sort of long-lived stable isotope, and they decay. And they not only decay, they decay in a very impatient way. So they gave off alpha particles, they gave off beta decay, and also they basically split up and then fission. So that's what the elements chemical synthesis works. So then this you will also hear for heavy elements or throughout maybe in Rich's talk, that so-called S processes and R processes. So this is referring to slow neutron addition processes and rapid neutron addition processes. So the way you summarize this is basically it's ultimately, in a nutshell, it is ultimately a competition between decay and neutron addition. So it is very difficult to add protons because of Coulomb barrier. So if you actually look at sort of so this is a nuclide chart for all the nuclides that we know of, and here's a plotted of the proton number, and then this is the neutron number. So in x-axis gave you identical chemical elements, and y-axis, and n is gave off for each element different isotopes, right? So as you can see, for the sort of light elements from hydrogen all the way up here, so more or less proton number and neutron number are close to 1. And then you start to bend off toward this direction. It reflects nature's easiness to add neutrons into, because you do not have the Coulomb barrier. So when you do that, the so-called slow S processes is, in next slide maybe it shows better. So here's I just take out one particular area of nuclide. So so-called S processes proceed like this in this yellow band, right? So you start from some nuclide, and then all of a sudden, when the star goes off, you have a copious amount of neutrons, and you add. So this shown in black is a stable one. So strontium-86 is stable. So you add neutrons, then become 87. Add another neutrons, 88. And then when you hit 89, that's only 40 days or so. So and then it will decay to yttrium. Yttrium add another neutron, and you have is at 1 hour or 64 hours, and then it will decay, and then you hit another stabilized of zircon and go all the way. And here you actually have a chance either to decay, that's 1.5 million year, or add another. That is considered long enough, right? Then you decay, and here you add another one, and then it will decay. And here you can add another one. That's 96, almost stable. It's 10 to the 3.8 times 10 to, and it will add another neutron, then it will decay. So this is a slow neutron process. You add one, and then you give time to decay. And this typically happens in so-called asymptotic giant brown stars. So our sun, for example, in 5 billion years later, will go through these stages later on. Okay, and then our processes basically occurs in supernovae. And what that happens is you just add copious amount of neutrons into entire periodic table, basically. Then you go all the way up to your left, right, until you reach some a boundary line, so-called neutron drip line. And then the rest basically is just following this decay trend here. So as you can see, then in this case, some of the nuclide would receive both S processes as well as our process input. But for example, molybdenum-94 here is blocked by the stable zirconium-94. So in this case, zirconium-94 would block, so 94 will never see that. For example, 96 is blocked by zirconium, so molybdenum is S only, not R. Okay, you will not see the contribution from such. Then there is in this case, these 4 stable isotopes are blocked by all these passes. So those are, nature sometimes manages to squeeze some protons into it. And typically, if you look at the abundance of those nuclide, the abundance is very, very low. Yeah, bad.
So this is really cool. But can you go back one slide before? Because on it you had this valley of stability, And maybe this is beyond the scope of this talk,
Okay.
but I just couldn't stop thinking about why is there that patch of yellow, which I assume is low stability. I guess how long the things last, right,
Yeah.
is colored.
So, yeah.
Why
So-
is it there? It's weird.
So that's why it's a value of stability. So it's
No, but the yellow, the interruption. You see? Right,
Here?
right. No, go up. Up, right there.
Oh, here?
Yeah,
Oh,
what's that?
Why there is?
Yeah.
So that okay. So basically, that's the last two elements is lead and bismuth, right? So nature managed to make stable nuclide up to there. Anything beyond is basically it's going to decay. Nature managed to make it, but then the yellow is only like here. 0.1 second and 5 seconds. They exist and then they decay. It's just unstable. Like I said, when you manage to make very big ones, the nuclear binding force is beyond the short range to hold them together, so they disintegrate. And then one above that, the only one element in there is thorium-232 and uranium. That's what it is. Yeah. So through some careful analysis, actually we can tell apart because S and R is added together, and you can actually tease apart those, right? As cosmochemists find those pre-solar grains, and they're made in a particular stellar environment, and in this case is silicon carbide grains, and solid here is a measurement, and then open symbol is a theoretical calculation, how much, given this particular neutron doses, how much you can actually produce. And that's the isotopic composition that we can measure, shown in part per 10,000. Right? So here is a huge effect in those pre-solar grains. And then, again, through some careful arrangement of isotopes, and here we normalized pure S process here only. So when the shown in flat part area is just average composition of the Earth, so which would combine both S and R in one element together, right? So then you have some excesses in certain materials, and that shows there's R process excess in this. So you do have now you establish that chemical inventory is a mixture of these processes.
Yeah, I had a question about. To do these calculations, I'm just trying to understand on a conceptual level. To do these calculations where you're predicting the abundances of these isotopes, don't you need to know something about the size and the details of the star that blew up to make our nebula?
Yeah.
Which is no longer here, obviously. So how do you have any?
So what you do is,
do
for this actually theoretical calculation for S process asymptotic design branch, I think it's fairly robust these days. Supernova is a difficult one to do. So what you do is give a particular mass, right? And then we know the cross sections that nuclear physics can measure, and then particular mechanism of producing neutrons. So in particular stars, there's a carbon reaction gave you a certain amount of neutrons, and they can predict in that particular stellar environment, given the temperature and how the nuclear or the network of nuclear reactions proceed, and then they can predict. So by measuring this, of course, and matching those theoretical calculations, we will be able to pinpoint this population of grain coming from particular mass stars, and this particular group of coming from another one. Yeah.
So does the agreement of those predictions with the measurements, does that tell you something about the mass of the star that blew up to make our solar system?
Yes. Yeah.
Wow.
Yeah. It's so that's how we know that this particular so-called pre-solar grain is pre-solar.
Okay.
It's coming from very particular stars. So when you do that, actually, there are about easily 1,000 stellar sources has contributed to our solar system inventory. Okay. So here's a sort of conceptual model. You have a red giant producing debris and supernova producing debris, and you have a molecular cloud, and you get collapsed and then collected in the meteorite, and you go through this so-called burning down the haystacks and find the needle processes, and you find a few grains, and you make the measurement, and we basically unravel this kind of history. So as a geochemist, this is what we mostly do. So you live with a group of stabilized abundances, and then there will be some radiogenic ingrowths. In this case, I'm using neodymium example. You have in one case is 100 billion year half-life for 147, and here is 146. Samarium has 103 million year half-life, and recently I think there's some controversy whether the half-life is 68 or 103.
The correct half-life anymore.
Right, yeah. It could be 68 million year.
68.
Yeah.
To 68.
Yeah. All right. So this is one way we do this. And another way we use isotopes, I think later on, Anat will be talking about the stable isotopes. And for a very long period of time, we thought the stable isotope fractionation only occurs in light elements, right? So in carbon, oxygen, and so on, and used as to unravel the physical-chemical processes. When you go through that, you learn about the physical-chemical process, pressure, temperature, and et cetera, et cetera. So now all of a sudden, cottage industry is developed because of the new technique of measuring, ability to measure isotopes. Or entire periodic table, basically, all of a sudden became up for grab. It's like exploring Wild West, right? So it's you sort of pick your favorite elements and learn about this heavy isotope enrichment and light isotope I guess I meant enriched here. And relative to reference standard, and we learn a lot about the physical chemistry, about the Earth. I think that will be Anat's talk. And then other people would do on top of this, this is inventory, and then you try to figure out to what fraction is coming from R processes and to what fraction is coming from L process, or S processes, and P processes, the proton-rich processes. So this will give us some idea about the solar nebula and the disk heterogeneity in the environment, and the level of mixing, et cetera, et cetera. So we are able to basically claim and pinpoint from the meteorite record a particular reservoir is different from one way from the other. For example, the Earth is a particularly spectacular example that seems to be very unique object that somebody asked whether one can simulate using the chondrite composition, and in fact, some people have done that. You have some 100,000 combinations of meteorite composition, right? And to try to satisfy the Earth, and there's no unique solution. So it tells you difficulty and perhaps the uniqueness of the Earth reservoir as one versus the other. Okay, so this is a
quick question.
Yeah.
How do you distinguish between red and blue? So you measure 146 neodymium.
Right. So yeah. So I guess this message didn't come across well enough. So here, first, you dissolve whatever you can, and then all the residual material, those are the refractory silicon carbide stuff that you do not dissolve with acid, and then you measure those composition, right? And those sort of, when you see this kind of matches with a theoretical model, then you know the S processes pattern should have that. And then this is Earth, which we know is a mixture, which is standard, right? So whatever is missing, because you have to add up. So this is a deficit, and this is excess, and you just add them up, and you basically, for each isotope, you do the mass balance. So you have very large isotopic effect, but the abundance of that particular grain has very low abundances. So for 94 mass balance, and this is easily like 1 gram of whole rock material that you measure, but the effect is only like a couple of epsilon versus minus 10,000 epsilon. So you basically do the mass balance to figure out how much is coming from R process, how much is S process, etc. So, yeah.
So these are anomalies, right? These are mass-independent anomalies. Sorry. These are mass-independent anomalies, right? So you know what the stable isotope fraction is just based on nature, and then you measure the mass independent, the anomalies, and then you can just do a subtraction. Say, well, we know we should have this percentage of neodymium 142 and this percentage, and the difference is just the mass independent, the anomaly. And these are really hard measurements to make.
So now a few words about the free fall time. So here's a very simple back on the envelope model. Okay, so suppose we have a cloud, right, with a mass of this volume times the particular density, and the only thing we did is here I did is a conservation of energy equation. So half of the kinetic energy and small m, you place a test particle of m here, and then let it go, right? And so again, small m cancels. So basically, you change the position from here at the outer envelope of the molecular cloud, and then you change into anywhere inside the cloud. So you just lose you just actually gain the kinetic, the potential energy and transfer it into kinetic energy, right? So then you integrate so-called, or you try to get this so-called free fall time, and TF, of course, is the integral of infinitesimal of dt. That's nothing fancy, right? And then on dt, you multiply it by dr and divide it by dr again, which is the same as nothing is done. So then here, dt over dr is inverse of the velocity here, r dot here, right? So you put in this equation in here, and you get these ugly integrals with minus square root, right, which is kind of difficult to solve. So you do twice a substitution where x is a fractional term with r over r naught here, and then you do another one. And when you do that, you can actually solve this analytically, and it comes out in this form here. So when you've done that, what you have managed to do is actually the whole thing, the time scale is independent of the initial size and independent of the mass, all right? The only thing it's dependent on is the density, and then the other is a gravitational constant there. So given a particular density of the molecular cloud, they will not stay around for a long period of time. That's universal again. So here you have initial density of 10 to minus 2 gram, and that's 1,000 particles of hydrogen molecule in cubic centimeter, and that is the best vacuum that we can actually hope for in mass spectrometry, right? It's out of nothing prepared, but this is considered by astronomers standard is a very dense molecular cloud. Typically, 100 particles, number density of 100 per cubic centimeter is considered dense in molecular cloud. And when you do that, actually this thing will collapse. Okay, so when you calculate, plug in this density number, and it's 2 million years, right? So what it means is a molecular cloud, interstellar medium, is a very transient feature. So you speed out from the stellar nucleosynthesis, and when they blow off and you produce copious amount of material, gas and dust, and then they move around. As long as they over critical density or the neighborhood, that thing will go collapse. And that thing will not go actually as one single object. There are so-called a Jeans criteria, and you actually split up and make a lot of stars. So sun is considered to be formed in a cluster, all right? And by accident, if one particular fragment of molecular cloud is massier than the other one, then the massive ones will live very short life and then produce freshly synthesized nuclide, which we actually see. So the thing is, so molecular cloud is very, very short and transient, and 2 million years, though, is considered relatively long. The reason is we actually detect inside the solar system radionuclides like aluminum-26 and calcium-41, and their half-life is 0.7 million year and 0.1 million year. And if you actually, there's another rule of thumb for any radioactive nuclide to be really effective chronometer. When you are after 5 or 6 half-life, you just run out of steam, and that clock will no longer be helpful for you. So the reason that we actually detect aluminum-26 and calcium-41 within solar system matter, that means a star has to produce that and make it travel and intercept it by the solid angle of the solar nebula and collect those and then made into solid. And that time scale needs to be all done within 5 half-lives. So this is a 5 or 6 half-life. We're talking about less than 1 million years now, right? So that would require some supernova explosion basically trigger and help to squeeze the molecular cloud in a much faster time scale. So that's one rule of thumb how we apply this. And another thing, when you look at actually typical radionuclides that we use often in geochemistry, uranium-235, which has 0.7 billion year half-life. As a result, after 4.5 billion years, uranium-235 sort of induces a flat area. So if you look at the modern basalt, mid-ocean ridge basalt, 207 does not vary. All right, and the only thing varies is 206. And another thing is, yeah.
Do you have an idea of the distance of propagation of a blast of a supernova within 2 million years?
Yeah. So, in a way, you can calculate that, right? Because we know how much we inherited, for example, freshly synthesized material. And when it's blow off, they will blow off in basically sending out 360 degrees all directions. And then some distance away, you have solar nebula. Basically, it's a very small solid angle intersecting that. So if it is close, very close, then you will have more material to receive. If it is too far, you will require long travel time and or decay time, et cetera. So based on the observation somewhere, so there's a sort of so-called dilution factor. Typical calculation, I think, is like a couple parsec away and so on. And another thing I meant to mention is hafnium, for example, is 9 million year half-life. So if you push this clock to beyond, 6 times 9 or 7 times 9, or we're talking about 60 million years, you basically run out of steam for hafnium-tungsten clock to be effective, and that will come out, I think, later on, right? So trigger star formation is required here, and astronomers, when they look at young solar system in the making, or what they see is something like this, right? So the only thing they can observe is a photon, of course. So here's a molecular cloud, and they can only, this is not particularly bright, right? And then here, sort of central star ignite, and you have the Planck curve of light curve. And on top of that, early on, during this disk formation, you have copious amount of disk and re-emitting in infrared region. So you have big shoulder on top of the standard peak of the light from the central star. You have a peak. You have this very bright infrared re-emission from the dust. And this they classify as a class 1 stage and class 2 stage and class 3 stage, and this thing proceed. So for cosmochemists to associate with this, with a meteoric record, for example, using the calcium aluminum-rich inclusions that Bill White mentioned and Qing-Zhu that he mentioned, we try to associate this kind of time scale that astronomers infer with what we can observe 4.5 billion years ago in laboratory. So can you imagine 4.5 billion years ago, this meteorite like this would witnesses the entire processes. This is like an artist's rendition of the disk, and then you will organize into a very orderly fashion. All right. And the observation, astronomers' observation, is something like this. So the disk fraction, the dust that they can measure. So when you have a lot of dust, it's 100% dust. It's a time 0. And all this dust, when they organize into planets and big planets, they're no longer able to observe the light from that object. So you can see that it is quickly decays, right? So what that means is a planet formation in that disk proceeds in a very fast fashion in that kind of time scale. Of course, our solar system should be no exception. And notice that each data point is a one solar system like us, young solar system in the making, right? here is our starting point. We are using sun as a sort of chemical reservoir, the starting composition. And again, the argument was made that this is a 99.87% of the entire current solar system mass. And we have a meteorite that really matches the sun's photosphere composition, so it's almost 1-to-1. Of course, you won't be able to measure concentration of sun's photosphere, so you have to have a normalizing scheme, and in this case, it's normalized to every million atoms of silicon, and then you convert the concentration from meteorites that you can measure. And when you do that, it's almost 1-to-1 for those refractory elements. So this is and I think Bruce was the one who commented out, but this is a log scale, right? So here I just basically flatten it out. So this is a normalized composition here. And this is still log scale. And you can see that, of course, rare gas would not match because sun is a gas. And this is a stone here, right? Here is actually the linear scale here, right? And of course, there are some large error bars. And that large error bars is actually not the geochemist's problem. It is an inability of astronomers to measure the chemical composition in the sun's photosphere, right? So imagine, it actually is really a better proxy that you use this to characterize sun's composition, because in lab we can measure this in less than 1% or something like that. So if you think about it, entire chemical processes, or whatever process, physical processes that happens since the beginning it's all about, from geochemist's point of view, is about destroying these beautiful relationships, right? You form the planet, you form the core, you just redistribute the chemical elements in there, right? When you destroy that, of course, nature will do some sloppy job, and with traces. So in this case, for example, you have residual mantle. You start with this primitive mantle composition, for example, right? And then you melt the stuff, and then you make continental crust. You make oceanic crust. I think this answers the Kanani's question yesterday. Residual mantle would look like this. And when you plot this concentration, C over normalized composition of the particular sample in particular setting, normalized primitive mantle, and order those as a function of D, which is a partition coefficient, a fancy way of chemists saying the concentration in solid or concentration in liquid. And if you look at, in this case, the elements were chosen only those radioactive elements, and in this case, it's this 4 pair. When you do that, now you have basically develop 2 points here. You have starting composition, you have particular parent-daughter ratio, and then you fundamentally alter that, and whatever the geological processes alter that parent-daughter ratio, then we have one equation, 2 unknowns, and we have 2 samples basically here to be able to uncover whatever geological processes that you're dealing with, right? So, we have tectonic engines like this on Earth. We have a tool to uncover entire processes with those kind of clock. So that's kind of a quick rundown. Then let me give the second part, a so-called standard model of planet formation, terrestrial planet formation in 3 stages. So what you have is a starting gas and dust. Then they will start to coagulate, right? And you have rapid growth. And this part of the history is not fully understood, and it's an active area of research. What I try to depict here is all those small dots are not differentiated yet. So we are talking about chondritic parent body here, right? And then later on, if you actually keep going, these things up to about 20 kilometers and 100 kilometer size object, and basically gravity kicks in, and then you can actually describe the remainder process fairly well. And back on the envelope calculation would tell you that the planet's growth would proceed in something like this. So you are diminishing number of objects, and it's sort of like a free market economy here, that you have thousands of small companies doing really, really well, right? And then you do not have enough. When you grow a body, large enough, you are reducing surface to volume ratio, so the heat cannot be released quick enough. So then the melting would ensure, so the metal silicate segregation would happen. And then not all the company would do equally well. Some are doing better than the others, and some will bankrupt. Some others will be basically sold, and some others will be doing better with their capitals. And that is basically gravitational focusing. You just collect all the materials as you go. And then you sort of sweep up in the terrestrial planets about 20 Mars-sized object, right? And all of a sudden the object collision chance is greatly diminished, right? Then you run out of supply chain, right? You don't have materials, right? And for the mutual survival, you merge. So you have United Airlines and whichever merge, Mobil, ExxonMobil merge, et cetera, et cetera. So that's the giant impact stage. And that time scale typically is 10 to 100 million years. Yeah.
So I've always heard that, and I don't know if this is correct,
yeah.
The stage 2 stuff is not well understood at all?
The stage 1, here, this part. Okay. This part, I think, is fairly well understood. Actually, one can do back-on-diagonal calculation. It comes out, you can calculate, get Safronov. Yeah, it's basically gravitational focusing, collecting all the materials, etc.
Okay, right.
Yeah.
So you could give us length scales to define those stages. When does dust become an embryo at what size, and when does gravity become important at what size?
Yeah, so gravity becomes important about, like I said, 20 kilometers to 100, basically boulder, mountain-sized object. Then it starts to take effect, and that is also the time you start to melt because you cannot dissipate those aluminum-26 radioactive heat fast enough.
Is it true that from the several centimeter to several meter size, that part is not very well understood?
It's very, very difficult, and it's because you lose them. When there's a sort of threshold size that when it's a so-called a meter-sized barrier, when you have meter-sized boulder built, they will just shoot at the sun. Because they at that time the gas does not disappear, so when you do the Kepler rotation, you face the headwind, then it will spiral in, and that's a meter-sized barrier. People did not figure out how to overcome that yet. Yeah, but pioneers like George Weatherly say, well, life goes on. After we see asteroid, we see Vesta, etc. So then we move on from beyond that, and that's how this part is sort of better understood. So my job here, yes.
Are you going to introduce the role that might have been played by the gas giants?
Probably a little bit later on. What kind of aspect you want to comment on?
That actually addresses some aspect of Alan's question.
In what way?
In terms of in terms of your domestic economies, also, we have outside or international players.
Right. That's right.
In this case, it's the gas giants in shaping what happens in the inner solar system, and you are actually imaging only the inner solar system here.
So the role of gas giant is something like in 1 or 2 minute summary would be look like this. So there's a snow line because of heliocentric distance away from the sun. So after certain distance away from the sun, there's a snow line. So beyond the snow line, basically water will condense. So when you have water condensed, you have a lot of water boulders forming outside, and that's the same as planetary embryos like this sort of start to coagulate. So you can actually form gas giant or initial core, 20 Earth masses, very fast. When you do that, then you start to retain the gas before the gas is blown away by so-called T-Tauri phases. So when you form gas giant, right, ever so slightly moving that gas giant in and out because of angular momentum conservation would send a lot of material inwards or outwards, and that helps this part of sort of overcome this kind of barrier. And there are series called asteroid formed big, or is that I think you are trying to allude to more or less, right? And gas giant, of course, when they're moving around, also produce a lot of shock waves and also helps to potentially as one source of making those silicate droplet that chondrules that Bill White was alluding to. Yeah. Did you have? No. Okay, no. All right. So now my job is using. So this is a stage setup and using the chronometer to unravel the time scale here, right? So we get the sort of production in stars. We establish that, and they will spend some time in the interstellar medium, very briefly, right? And then the collapse occurs, and the solid will be locked in. So once it is locked in, all the radioactivity is locked in, the only thing happens to them is a radioactive decay. So here I illustrate using 182 tungsten or manganese 53. And our goal is to measure the amount of radioactive 53 or hafnium is left. And from between T1 and T2, you compare the level, and you basically back out the time difference in this case, right? So here is a typical rulers that you select. So each system has a unique, is being uniquely affected by their particular geochemical property of parent and daughter elements and applicable for different purposes. So for example, if you want to date materials rich in calcium and rich in aluminum, you know what kind of material you want to look for, right? If you want to date volatile element depletion, which is a very big phenomena in the solar system, you want to pick a system like this where one element is more volatile than the other, right? So you pick your ruler. And the ruler, there's also different sizes. And if you are looking at cross-mental differentiation, the Hadean part, where the 500 million year Earth history, the rock record is gone, but we can still uncover the isotopic signature from that dark age of first 500 million. You may want to look for something like this, right? And this is the typical abundances that has been observed. All right. So in this case, I'm going to use manganese chromium system as an example. And manganese 53 decays to chromium 53 by electron capture. The half-life 3.7. So that's, again, remember the rule of thumb for 5 half-lives. So we're talking about the 15 million year windows in the beginning of the solar system. And this pair has a very ideal cosmochemical property. Manganese is moderately volatile, not very volatile. If it's too volatile, it will be difficult to handle. And chromium is relatively refractory, so it's a good, and it's a major element, right? So we're talking about some major processes. So next, I'm going to introduce in a little movie how the chronometer itself works. So let me just quickly write down what we're doing here, and then. Let's see if I can. So I hope everyone can see this. So this is what we can measure, right? And then we have 53 manganese parent, which is decaying to this, right? It's only 3.7 million and a half, so 100%, everything is converted to 53. That's what we're measuring. So this is what we can measure. What we don't know is when you started it, there's some finite amount of initial 53 chromium was there, right? And then after that, there's, in addition, remember that little extra red that is added as a radiogenic ingrowth. So that's the equation, this simple equation, right? And of course, a chemist has a very difficult time to measure the absolute amount. So you have to always ratio this. And in this case, we are ratioing this to chromium 54 stable. And here is a common denominator, chromium 54. And chromium, 52. So that's what we have. Right. So this is a very not so impressive equations. So this is what we measure. We can measure in the lab up to the 7th decimal point, very, very precise. This is some initial ratios that we don't know, so unknown. And we also want to know 53, how much 53 was there at the beginning of solar system, on that particular rock that you're dealing with, or that particular planet that you're dealing with, how much was there. So you have two unknowns, one equation, and this is only measurable quantity. So you run into problem. And what we do then is multiply manganese 55 and divide it by manganese 55. Manganese is a stable nuclide, a mononuclide, and that's the one we can measure. So when you do that, this is something that we can measure now. It's a chemical elemental ratio of manganese over chromium. That we can measure. Now here is a radioactive manganese 53 over stable manganese 53 is our unknown again, right? So still, we have now increased the measurable quantity to 2. This is measurable quantity. And we still have unknowns here, and we want to uncover this. What we need to do then is basically try to get another minerals. So shown in here, you have different manganese chromium as long as they formed at the same time, or another object, planets or core or whatever that you pick. So now you have, as long as they formed at the same time, this equation would apply. So you change the parent-daughter ratio, and then as a result, this thing will change. And when you document the differences in chromium 53, then the system is fully solved. And of course, we measure more than 2, and then you go through this error minimization of the isochron, etc. So here it schematically shows. Thank you, Barbara. So here's three minerals. One with low manganese chromium, one is intermediate, and one is high. And now I'm going to run the clock. So what happens is, as long as they formed at the same time, they started with same initial. And as the clock runs, 53 will grow, and the high manganese 53 will grow longer. And as you can see now, the clock is still running, time is going on unidirectional, but this run out because you are beyond 5 half-life, right? So it's no longer growing. So this is called fossilized isochron. You're sort of frozen in at that point in time. So now we found from this slope, we found the level of 53 left in that particular object, right? In the solar system, you pick any particular rock. Imagine you run another meteorite beginning from the solar system, and you have somewhat different slope. With that, now we have ability to calculate the time differences here, right? So manganese 53 from blue compared to manganese 53 from the red, sample 2. And the only thing is just a radioactive decay over time. And what you see is we can only, with this system, we can only determine the relative times, delta t. We actually do not determine the absolute age because those are gone. So we don't really know for sure whether that formed 4.8 billion years ago, 4.4, 4.5, or later on. So we need another constraint, an independent constraint. So this is where the short-lived radionuclide must be anchored into a sort of longer ruler, longer time scale. And this is where the second rule comes in. So what we need to do in this case then is you select a few milestones of rocks, which is very well behaved. You do not have a lot of extended metamorphism. You have very punctuated time, and you need a very pristine crystalline rocks, and we do have quite a few of those. And Daubigny angrite is one of them. So, and you determine the absolute the amount of manganese 53, and in this case, those rocks independent also have absolute ages, right? Absolute ages dated by uranium lead system, and uranium lead system is only long-lived chronometer with comparable age resolution compared to the short-lived radionuclide. So we are fortunate that uranium lead would be able to serve as a absolute chronometer to allow us to anchor this level of radioactivity at absolute time scale. So when we do that, here's what we ended up finding, right? So a random solar system object, okay, we measure the level of manganese 53 and document and then expressed in the log term here. And here is a lead absolute age, right? What you can see is that they align on a line. So basically the slope, according to the equation, would be basically the half-life, right? So the blue line is what the decay constant half-life on this grain should be. And we have documented now the every single object basically following on this line. So what it means is that we have, these are all random meteorite that is floating around in the solar system. What it means then is the solar system inherited the same amount of manganese 53, right? And then basically the only thing that happens ever since is decaying, radioactive decay. So we sort of established that the chronometer indeed works. Alternative to this is something like if you have multiple supernova is blowing off and you have patches of manganese 53 at different level, and if you are in that kind of mode, then you are in trouble to using this short-lived radioactivity as a chronometer, because the particular accident of stars produce two stars blowing off at the same time, but producing different amount of manganese 53 or 26, you name it, then you will not be able to use as a chronometer. So establishing this kind of relationship gave us confidence that actually both the short-lived radionuclide actually works exactly as predicted. So here's another example for alum-26. So here's a time scale that relative ages alum-26 that we can measure in different objects. And here is a lead ages. So you can see that the whole entire time span here is 8 million years at very beginning, and here is another 8 million years at the very beginning. So that means both chronometers are giving identical information. So with this information, now we know we can confidently apply this short-lived radionuclide to date particular events in the solar system. So here is, we have seen this in Bill's talk, carbonaceous chondrite, or cosmic sediments, that you have calcium armor-rich inclusions, and you have chondrules, and then you have all these low-temperature matrix, pack them together, right? And the question is, first, what are these individual objects, when they form, and then how the undifferentiated object as a rock, whole rock, form. So that's the two questions. So first, the dust age is very well defined, and we can sort of anchor this at time zero with plus minus 20,000 years kind of resolution. So that's a first time zero piece, the solid object that we ever be able to measure.
Which meteorite is this?
This is Allende in Allende CAIs. And here's again chondrules that we also measure, right, from this kind of slope that we can translate into absolute ages. So more important question is, once you have those sediment grains, and how do you actually, at what time you actually pack this into a rock? So you have, you're witnessing this kind of processes, and you have parent body, and by impact ejection, we happen to have an object like this, and we want to date at what time scale that these things came to be, right? And here, a manganese chromium system can help out in a great deal. What happens is this. So again, carbonaceous chondrite, and here's just a matrix fraction, the black stuff, the percentage of black stuff. So for example, the CI particular type has no chondrules and just 100% matrix. 100% matrix, and it turns out to be having highest volatile to refractory element ratio, right? It's 0.9-ish. And then here you have variable amount of the refractory component in there. And here is another extreme example that basically you only have the refractory component and you have hardly any the matrix material. So you have a group of material that has experienced a volatile depletion at the beginning of the solar system. The question is, can we uncover, given the range of manganese chromium ratio, parent daughter ratio, can we uncover the age information from here, right? So, and we have done that. And those are shown in these blue dots, right? So manganese chromium ratio changes, and it gave this particular slope, and now we know this particular slope can be translated into the relative ages and compared to the anchor, and can be translated into absolute ages. When you do that, this is a time scale. So we're talking about this part of this accretion must have occurred and completed within, from time zero, within 1.3 million years or so. Right? So now stage one is now complete. Yes.
You're relating this to planetesimal formation. But would it also be fair to talk about when volatility was imparted into the residual materials?
So, I mean, that's a part. I guess it's a part of these processes, right? So, when you form these kind of things, this is ianda is a CV. You just incorporated different amount of the volatiles in there, and here is you have a much more volatiles, and here you have low volatiles altogether, right? Yeah.
Okay. Much more from a historical perspective. Perhaps some of the students might appreciate this, but earlier models for planetary formation involved the bringing together of particles, maybe they're big particles, and some people have conjectured that a very large C1 chondrite planetary body was formed, and through the impact process lost their volatiles. Whereas, so you could, and it has been proposed that the Earth was formed and it went through a volatile loss stage. It is your information and others from the field who have brought the chromium data to show that it was a early process.
I don't think the impact process in the parent body would really vaporize at this level.
It's historical that this idea was out there.
Especially if you think about when they come in on Earth, they also go through the impact processes, and it's only the skin of layer that was affected, right? So now hopefully I have defined the stage one as absolute age. Yeah, Quentin.
You've kind of assigned a single age, and that's very powerful for these processes. But is your physical instinct that there should be a radial dependence outward from the sun, and the rate of formation from gas to dust, in particular, as there's likely to be a change in geochemistry prospectively as well as you move outward within the solar system? Yeah. That is, what is the radial dependence of this?
Yeah, I'm kind of, it's difficult to gauge from a suite of carbonaceous chondrite have a radial dependencies, right? Because if you think about it, these guys are probably coming from the outer C-type asteroid belts. So that's we're talking about very small range. But the scenario can change if you actually consider some of the CIs is actually the cometary parent body that came through the angular momentum exchange with giant planets came from cometary or Kuiper belt and came in. Then we do have a bigger scale nebula-wide volatile depletion trend that is recorded by this slope. But in terms of range, I'm willing to give in. It has to occur in this range. Yeah, it's done within this range. That's how I can resolve, right? Yes, that.
So earlier you did a calculation that showed that the collapse of the gas cloud would be on the order of a couple of million years. So should I think of, and then you showed that it's the supernova additions that are maybe triggering the collapse of the cloud. But now you're saying that we have to complete stage one within 1.3 million years.
Right.
Does that mean that the original gas cloud had a very high density because that's the only way you can collapse it more quickly? Or does it mean that it was already collapsing and then you added some stuff from one super?
So that gave me opportunity to clarify this. These are two different time scales. So the collapse, once you collapse, and then in the inner part, the dust get vaporized, and then you start to recondense those rock. So this time is actually coming from after collapse, and then counting onwards. Yeah. You do not actually. So the collapse time is actually from the pre-solar dust and gas that is collapsing.
Well, we know
and then,
had to happen while there were still these really short-lived isotopes
yes.
alive.
Yeah.
So what's the longest that it could have taken?
for you to actually gauge that part of the window, you would need to, it's a kind of model dependent, then you have to calculate how the star is producing at what quantity. Right? So what we can do now is basically meteoric record from that we have in hand today, and we try to gauge from time zero how much it has elapsed. So this is after the dust formation within the solar system, you reprocess. So now it's a CAI and chondrules are all solar system material that you used prior generation of dust as your raw material, and you melt it and you restart the clock. That's the so this 1.3 is a different time scale versus the collapse time scale. Collapse time scale refers to sort of earlier on what went on. Yeah. Okay, so this is my stage 1. And stage 2, in a very simple manner, I will use a Vesta and whole suite of differentiated object that I think nobody would argue that by about 3 million years this is done. And this old slide where we use a bulk silicate Earth using hafnium tungsten in this case. And I think the moon's data point is now updated, and we sort of calculate with the giant moon-forming giant impact as well as core formation must have accreted and done by about 30 million years. It's a simple two-stage model. And the way you think about it is something like this, right? So look at the Earth as a two-mineral rock, right? You have one mineral called metal, and you have another mineral called silicate, right? Two minerals. So two samples now, right? And one equation, two unknowns, and you have two samples. And we will never be able to reach the core, so we use a chondrite as a beginning composition. So you still have two samples, right? One is a chondrite, one is a silicated mantle that you can go out and pick, right? So it turns out that the hafnium tungsten ratio of the total Earth, which is equals to the solar system, is just 1, right? Then hafnium tungsten has this particular property that tungsten is siderophile, so when you have a core formation, tungsten gets pumped in, and hafnium does not. So your metallic core will be having hafnium tungsten ratio 0, and the silicated mantle would be 15. It's very, very high. You pumped it up, right? So again, if you look at the radiogenic ingrowth, this curve would grow like this. So suppose sometime within the lifetime, before hafnium tungsten was really extinct, you separate the silicated mantle and you separate core. The core would be freezing in, and then you just record that particular point, red points in time, right? And then the silicated mantle would grow more radiogenic than your bulk chondrite composition. So that's the expectation. So this was actually documented finally after many trials and errors in 2002. And what you have is something like this, right? So you have chondritic bulk Earth composition is here, and then silicated mantle is sort of well resolved and above. And that means, gross time scale, that metal silicate segregation must have occurred within this window. So that's the only conclusion that we were able to draw at the time, right? And of course, there are complications if you think about it. You are the third stage of planet formation, you are talking about merging at least 10 Mars-sized objects to make one Earth, and another 10 Mars-sized objects to make the Venus, right? So 20 Mars-sized objects. So they go through this kind of giant impact stages multiple times. And chances for chronology to work, of course, you have to reset the clock every time when you do that, right? So then you can count. If you do not, then you sort of inherit the earlier radiogenic ingrowth information that complicate the picture. So whether during these processes metal and silicate is fully chemically equilibrated or not was called into question. And of course, it goes through this. When you dump the energy, it goes through the magma ocean, and there's a lot of argument were made whether the magma ocean really go all the way down to the core mantle boundary or halfway into the mantle, about 1,000 kilometers in average. And this is, again, a cumulative effect of multiple giant impact, et cetera, et cetera. So there's a smart man, John Raj, Dan McKenzie's student, I believe, right? And he modeled these processes. And in addition to this exponential accretion model and the sort of two simple stage model, what he has done is he put into the parameter called disequilibrium degree, so which is K. If it's 1, that means it's every time when you do it, it's fully equilibrated stages, and you allow this to vary, right? So basically, whether it's a 2-stage or exponential accretion model for the planets, when you build up, what he came up is a curve like this. So you run into basically a dichotomy. So the solution space right now is either you are in this part of the space, right? You allow a range of chemical disequilibrium from full equilibration to up to perhaps 40%. And when you are in this regime, then almost certainly the accretion time and the core formation time and moon formation time is very, very early. Alternatively, hafnium tungsten tell you nothing about the age because you are in the flat part of the region. Remember, 180 tungsten is now run out of steam. So if you are in this stage, then what hafnium tungsten tells you is not about timing, but about the degree of chemical equilibration, that somehow you only manage to reach 40% of equilibration in average, during the planetary accretion, the 3rd stage. So this is where the field right now is. And I can develop more I actually developed some argument that actually there's evidence from how much we can squeeze light element into the core, and does give us some hint about how much you can actually establish chemical equilibrium. But that has to be a separate talk, so I put this thing aside behind. Yeah.
Sorry, I actually did not understand that at all.
This part?
I'm sorry.
Yeah. Go ahead.
It's selfish to ask for my own sake, but maybe someone else didn't. What's K?
So when you have metal comes in, or maybe let's see. So here's a K. So you have embryos coming in and collide to your target, make the planets, right? And you have some chunk of silicate will added into there. And metal can either, some fraction of metal will go into the core directly without interacting with your mental envelope. Some fraction will go in and interact with the metal, interact with silicate mantle and then go in. So this sort of more realistic processes is modeled by him. So this is a K. K is a fraction of metal from the impactor coming in, how much they interact with a target mantle. Yeah. So back to my So this is where the field is stand. I'm not going to give you my biased view. If you want to hear about it, I will be more than happy to give a full argument about this, why I think we are in this region rather than in this region, right? But this is where the field is now, and there's a lot of, work was done trying to understand the physics of these chemical equilibration processes. Please. Anyone has microphone? Oh. Yeah.
They know I don't need one. No, how sensitive are these results to the partition coefficients, metal silicate partition coefficients of tungsten, for example?
Okay, so actually, this range is basically governed by partition coefficient uncertainty that is known based on the literature. Yeah, this curve.
The width of the pink?
Yeah, the width of the pink. Yeah. Quentin.
I don't. Do I need a mic? Yes. Okay. One of the bills yesterday or the day before alluded to impact-induced erosion. Oh, it's off. Okay.
Right.
One of the bills alluded to impact-induced erosion, Would that impact these inferred chronologies if there was pervasive impact-induced erosion of, let's say, the hafnium associated with this? Would that move you off the chondritic model for this? And how much would that impact?
That part is actually not visited yet. I don't think we don't have. I don't have a good feeling how that will actually factor into.
Erosion would be happening very early, more in the vesta to Mars size range of the embryos and planetesimals that ultimately form the Earth, rather than these late giant impacts. By that time,
are you sure of that?
I'm not sure, but the reasoning is, well, there's a couple things. One is you really need to do it. You need to do it because of the short half-life of samarium 146. You really need to do it fairly quickly, within hopefully a few million years. That's point number one. Point number two is, as you grow the planets, as these bodies become bigger, it becomes a lot more difficult for the ejecta to gravitationally escape. So at least that's my reasoning. Those two ideas are why it's likely to happen earlier rather than later in the early stages of planetesimal formation.
Simon.
Dynamically, I'm going to start my sentence with that. Collisional erosion is something that the jury is definitely still out on, because in order to get the isotopic effects people want, you need to remove crust in preference to mantle. And that is not something that is obvious from impact simulations that you can achieve that. And it's not necessarily obvious that that would be easier earlier on than later, because you have a trade-off between, yes, the bodies are smaller, but your impacts are also less energetic, because you've still got gas around to damp your collisions, and you've got smaller bodies and therefore smaller collisional velocities. So collisional erosion is not necessarily possible. I just put that out there as a thing. It could explain some of the chemistry. It could complicate others. But on a dynamical standpoint, it's the jury's on whether it is actually feasible.
Okay, thanks.
One other thing I should say is that the Moon and the Earth have the same 142, 144 neodymium. That also constrains whatever explanation there is, either collisional erosion or sequester in the deep mantle, to have occurred before the moon forming impact.
Okay, Kanani.
Okay, I'm going to go back to both Liz's question and Ved's question, because I'm still confused about the differences between these two. Those curves look virtually identical between the two models. Yeah. So, and I think that K was
for good reason, actually.
So I thought that K is like the amount of fractionation that either had communication with the mantle or went straight to the core. Right. Mm-hmm. So in terms of partitioning, it sounds as if the stuff that went straight to the core, partitioning doesn't even matter, or like it never talked with the mantle.
That partition actually occurred in the prior body.
In the prior body.
Yeah.
So when two differentiated bodies come together, the core from one, most of it, I think, will just merge right into the core of the other and never see the silicate. So that's the idea, right? That's the 1 minus K. Just goes right into the core.
Okay, so it saw the partitioning beforehand. Okay. Yeah.
At lower pressure.
Different partitioning, right then.
That's why I was asking, because the tungsten's siderophility is a very strong function of pressure, actually, like the strongest that's been documented. So the fact that a lot of this equilibration is happening on smaller bodies at lower pressures would be, I would think that whether you did this as a single stage equilibration or the merging of cores from lower pressure differentiation would really affect the model outcomes.
But it doesn't appear to, right? I mean, do they look the same? I
mean, between these two models?
Yeah.
These two models is just sort of it's only about the growth mode. So one is basically you have a single giant impact, two body merge at one time. Done. That's the curve. All right. Here is basically you grow one by one, and exponentially grow the planets. When you do that, the curve would look like this. And basically, as you noticed, there's no big difference. So the point of showing this is that actually, single two-stage model is not that bad at all. It's another take-home, basically.
How?
Right. So here's the timeline. I hope I convinced you that first solid formed at that point in time, and Qing-Zhu, perhaps there are at least the first generation of Qing-Zhu formed at that time. There are some 2 million age gap that I have shown earlier. I don't know if you have noticed that when it's a class 1, class 2 object stuff. There's 2 million age gap. And I think we are on the way to erase that age gap. And you kind of need to do that somehow, unless some physics we don't understand. What happens is that if you have an object, CAI-sized object floating, and without losing to the sun, you have to find a way to store it somewhere in the solar system. Right? And that's very difficult to do. So when you have 2 million age gap, it's not easy to preserve those, and yet we have it in meteorite record. So stage 1 planet formation, as documented by this volatile depletion, I think is around 4566 and plus minus whatever. And stage 2 planetary embryo, represented by Mars or Vesta, is it's about 3 million years later. And the giant impact easily within the 30 to whatever you pick your favorite number, depending on which model you believe. So in my personal view, within the 30 million years Earth's history, right, we actually accomplished a lot. So we had a core formed, we had satellite moon formed, and that's what Hafnium-Tungsten tells us. And we have mantle is depleted. This is actually coming from the neodymium-142 work. And mantle is degassed. I think this is what Suzhou is going to talk about with iodine, xenon, et cetera, et cetera. And so that's pretty much covers what I want to talk about. If you guys want to hear more about neodymium, I'm more than happy to talk. This is where the stage of neodymium business, where it stands now. And you can see that the N-style chondrite, there are some group of N-style chondrite, is indeed like the Earth. And if the Earth and N-style chondrite, if we actually lose the ability to use a chondrite as a reference point, it has really a profound implication. Although it's only 20 ppm of differences in neodymium isotopes, what you have is you are either losing large chunk of material or hiding somewhere in the core mantle boundary, or you lose through the collision erosion processes. So we do need to find out what should be really the best choice for representing the Earth. And I think isotopic information has a powerful message to give. This is, should I go on or should I stop here? Yeah, you want to comment?
You don't like Bouvier's age for the CAI?
Which
is a little...
Yeah.
Bouvier's age would move that back several 100,000 years, the start of the solar system.
So, quick, that...
2 slides.
2 slides. Here.
This is what he's talking about.
Yeah, she's got 4, 5, 6, 8 point something.
So there's one paper published, is 4, 5, 6, 8 instead of 4, 5, 6, 7. What happened with that paper is actually they did not measure uranium isotope.
They did.
No, they inferred.
No, but I talked to her about that. She said she subsequently measured it, and it did not change the age.
Okay, anyway, 2 independent groups actually measured uranium, and they did not confirm that, so I don't know. In a sense, this doesn't really matter. It's just time 0 or whatever. Yeah. Maybe so I do have some reservation about that. Okay. So.